Hi class, it's Bill Berry here. We are starting into the next data structure of interest in our Java 2 course. We're going to start into discussing trees and specifically binary search trees. They will serve as the basis of our next project. This is a fairly substantial one. Trees are super interesting and useful for a lot of things in computer science and applications, so we are going to spend a bit of time talking about that. In this video, we are really just trying to introduce trees, give you the terminology, make sure that everything makes sense, and then we'll stop and take a little side journey about something that we need to understand, and then we'll come back and look into the code associated especially with binary search trees, and there's a good bit to that. We're also going to make use of recursion here, so we want to be careful, make sure we understand exactly what's going on as we get into this. So let us jump into the study of trees. So let us get into some of the terminology here. What is a tree? These are nonlinear data structures. So far, things that we've studied, like an array or even a linked list, tend to be linear. They tend to have an ordering that is very predictable, straightforward, and sort of singular in direction. But trees are going to be a little bit different. So let us jump into terminology for trees. First of all, what is a tree? Well, it's a nonlinear data structure, as we just said. Trees are accessed beginning at what's called a root node. Now, if you're thinking of a tree, you kind of have to think of the root system of a tree here or an upside down tree, because the root in a tree is up here, right? So we have a root reference. Just like with a linked list, you have a front reference. With a tree, you have a root reference. And that's going to point here to the thing that's at the top. And then, as again, you can think of the root system of a tree, they go down, right? From that point, the tree extends downward. So they're still directional, right? But they are not linear because a tree can have multiple of these children. So what are those children called? They're called nodes, right? So each of those things is called a node, again, similar to what we did with the linked list. And there are a couple of terms associated with that. One is an internal node. So a node is internal if it has one or more children. This is an internal node. So is this. So is this. And if it sits at the bottom, if a node sits at the bottom and has no children, it's called a leaf node. Again, we sort of have backward trees. If you think of this inverted, then these would be the leaves. All the rest are just little branching points in the tree, right? So these are the leaf nodes. Now, another thing that we need to do here is talk about a little bit of measuring. How do we measure trees? Well, one of the important things is that we can measure height, and that is the maximum distance from the root node, which is A in this case, to the maximum distance to any leaf node. Now, when you measure this, you don't count the nodes, you count the edges or the lines that are between the nodes. So we find the longest one that we see and we count the edges. 1, 2, 3. So this has a height of 3. 1, 2, 3, right? This far left side. Center, 1, 2, 3. Right? 1, 2. So since this is longest, these two both have heights of 3, then we would say this overall tree has a height of 3. So again, don't count the nodes, count the edges, or count the nodes and subtract 1 to get the maximum height. Your textbook has a couple of places where that's made a little bit murky, but that's how you measure them. The other thing to measure here is the number of children. So since this particular node has 1, 2, 3 children, it has a degree of 3. This one has 2 children. It has a degree of 2. That becomes important because we're going to talk about binary trees in a minute, and most of what we're going to play with is going to be binary. So we want to measure the height of a tree and also look at how many children each particular node has, which is the degree of that particular node. So hopefully all those terms make some sense. Now, speaking of which, we're now moving into the study of binary, or discussing binary, and a lot of what we do for our studies, again, will focus here. So what is a binary tree? Well, binary means 2. A binary tree, each of the nodes in a binary tree have at most 2 children. Now, that's not to say they all have 2 children. Sometimes they have no children, right? If they are leaf nodes, they don't have a child. And some nodes have 1 child. That's perfectly all right. You look over here, this one has 1 child, this one has 1 child. It's still a binary tree because no node has more than 2 children, right? This one has 2, this one has 2, everything's good, this one has 2. So that's a binary tree. More specifically now, a binary search tree, or BST, that we'll use as an abbreviation, that is a tree that has a very specific ordering of its nodes. So it is a binary tree, which means no node can have more than 2 children, but the values of these have a specific ordering with respect to its parents. The thing that you'll see is that the item that's in the left subtree, not just the element, but every element in the left subtree is going to be less than that node's element value, and everything in the right subtree is going to be more than that node's element's value. So to the left we have smaller things, and to the right we have bigger things. Now, if you're allowing duplicates, you have to decide, right? You have to decide whether to throw them into the left or throw them into the right. For a while here, we're just going to pretend that everything's unique, but you can certainly do that. But these binary search trees have this very specific type of relationship, and it continues all the way down the tree. So you can guarantee that everything to the left of any particular node is going to be smaller, everything to the right is going to be bigger. Now, look at this and answer the question of whether this is a binary search tree. So pause a minute, look at it carefully, and then resume the video and we'll discuss. In this case, you'll see that this is indeed a binary search tree. So if we start with 8, we'll see that everything here on this side is less than 8. Everything here is more than 8. Okay, so here we have a 3. Everything to the left of this is less than 3, indeed. Everything more than this, to the right of this, is more than 3, indeed. Everything to the left of this is less than 6. Everything more than this is greater than 6, indeed. Greater than this is bigger than 10. On to the right, yes, this is to the right side, notice. And everything to the left here is less than 14, and that is indeed true. So the numbers look a little bit odd to your eye at first, but in this case, this is a perfectly serviceable, true binary search tree. And of course, there are no nodes that have more than 2 children. So it is a binary tree, but it is also, because of the way the values are arranged, a binary search tree. Got that? So the other thing here is that when we look at how we're going to traverse the tree and how we're going to search, because a binary search tree's particular properties are going to lend itself to some very nice, unique ways, or cool ways and fast ways to get to data. So we also want to keep this tree height balanced. And height balancing just means that we want to keep it as close to possible where the left and the right have the same height. Now, often they won't be perfectly the same, but they have to be as close as possible, which means within 1. So, for instance, here we have the left subtree has a height of 1, 2, 3. The right subtree, 1, 2, 3. This is a height balanced tree. We don't worry about the fact that that little guy has 1 child over here. And notice we're not counting the number of nodes. That's not what we're doing here. We're counting the height of the tree. So go back and look at that definition if you need to. Does that make sense? Now, again, we're going to implement some algorithms that are going to make very quick work of searching for things in this tree. And if you think about it, knowing these properties of left is smaller and right is bigger is going to make those algorithms very fast. But we have to keep height balanced in order to make that happen, as we're going to see later. The only way to keep the algorithms as quick as we want them to be is to be height balanced, right? The tree has to be height balanced. So occasionally your trees are going to need to be rebalanced. If you build them from scratch, from data, they might be unbalanced, and if so, we need to balance those. That's a later topic. You have trees that either can balance themselves by code, or that you can periodically just decide to go through and sort of brute force rebalance. We'll talk about all that. But you have to keep it height balanced in order to keep the complexity of the algorithms where we want them to be, which is still darn fast and pretty darn cool. All right, so now let's look at one other thing, and that is, as I was mentioning, traversals. So let's look at typical ways that you're going to traverse trees. Right? You can traverse any kind of tree, but binary trees, especially binary search trees even more, are going to be traversed in a particular way. There's 3 different ways that we talk about that. One is called pre-order. One is called in order, one is called post order. So what do you do with pre-order? Now notice all of these things will discuss how right and left, right, and center work, but you never have any of these that go right before left. So that's one thing as a good little memory trick. You never go right before left. You always will do left before right, no matter which of the other orders you've got going. So what is a pre-order tree? You start with the root, then you go to the left, and then you go to the right. So I process the root, that's an 8. Then I go to the left, that's a 3. Then I go to the right, that's a 10. But remember, we're going to use recursive algorithms, so that's going to go process the root, go to the left. Okay, process the root, go to the left. Can't go left anymore. Process the right. Now traverse, again, recurse, go to the left, or process this, right, the root, which is 6, now go to the left, then go to the right. If you look at how we were doing that, you'll see that that could actually copy the tree. If you want to copy this tree exactly, you can do a pre-order traversal, which says, do me, do my left child, and then do my right child. And then recursively, each one of those is going to do the same thing. Right? Do me, do my left child, do my right child. So pre-order, one of the examples of what this can do is to copy a tree exactly as it sits. All right? You'll recreate it exactly as it sits here. There's also in order, which turns out to be a very convenient one that we use a lot with binary search trees, because look at what happens. It says process my left, then do me, then do my right child. So again, recursively, process my left, process my left. Okay, there's no more left, so here's the 1. Then process the root, right? So this was the left subtree, now the root. Well, now I'm at 3. And now I'm done with me, so now I go to the right. Okay, do the right. Okay, what do you do now? Well, again, recurse. So do my left, then do me, then do my right. Do you see what we've done when we said process each thing? We got 1 and then 3 and then 4 and then 6 and then 7, and then we will backtrack back to here. This is finally the process of the root here, right? Then we will do the right. So what does in order do? In a binary search tree, you will get out a list of node values in ascending order. Right? That will be a perfectly in order list of values. So of course we use that one a lot. You get sorted order. There's also a discussion here and a link to something called prefix notation. You may not have ever thought about this prefix and postfix. There's some really interesting topics about this involving portable personal calculators, battery-operated personal calculators, which we assume have always existed, but no, indeed, not as long as I've lived have they existed. And some of the early calculators had a very different way of you putting in numbers and doing operations on them. One is prefix, one is more postfix. So look those up if you want a little funny history lesson. But the traversing of trees that contain different kind of data, because trees aren't always just plain numbers like this, right? Sometimes there's operations and other interesting things. So interesting other things you can do with in order and post order, but I digress, so I'll come back to my other thought here. Last one is called post order, and that one is you do left and then right and then root, right? So you go left and then you go right and then you go root. So all of these trees can be traversed in any of these orders. They don't have to be binary trees even, right? They can be any kind of tree you can work in this order. Although this particularly talks about binary because we're only saying root, left, right. So this would be a binary, especially binary search trees. Okay, so let's look at one trick, because you may think, well, how am I going to ever remember this? Well, one good way to do this is to use your finger and trace a path that starts above and moves along, tracing as if these are islands, right? Think about these as islands, and maybe think of these little lines as maybe little sandbars. Maybe they're barely submerged, so maybe not sandbars, but they're certainly not passable, right? So you want to visit these islands, but you can't hit these sort of, this is not deep enough water here. So to visit all the islands, you have to sort of go around them and be careful to mind the sandbars, right? So you can go around them and then carefully navigate around these. Now, if you pay attention to the nodes that are On the left side of your finger, you get pre-order. If you are looking at the nodes that are, well, actually, no. Say this again. If my finger is on the left side when I write down the node, that's pre-order. If my finger is on the bottom of the node, then I write down, if I write them then down, I'm going to get in order. And if my finger is on the right side as I write them down, that's going to be post order. So we'll put the finger in motion and see if you can follow it. Okay, so let's take the in order version and see how that works, right? So we're only writing down a node if our finger is on the bottom of it. So we're starting up here, right? Our finger is not at the bottom, it's above it. So I'm going here. I'm not on the bottom of any of them yet. Oops, I'm on the bottom of this one. So I write down 29. Okay, now I keep going. Now I'm on the bottom of this one. I'm at 41. Now I'm at 6. Now I'm at 17, 81, 9, 40, and that's it. So that would be in order. Now this is not a binary search tree. Of course, if it were, then following that would give us an in order sorted list of our elements, but you can certainly use this on a regular binary search tree. So the position of your finger as you move through this, if you pay attention, will let you give pre-order, in order, and post-order readings of a particular binary tree. Does that make sense? So hopefully that's a nice little trick that will help. Now, we've got plenty more to talk about with trees, and we want to certainly start looking at code. The code for this is a little bit trickier, a little more interesting in some ways. There's more to it, so we want to actually take a pause and look at a particular concept that you think we would understand by now in Java, but it turns out our brains are really not quite prepared for it. So we're going to take a little pause to talk about a particular little algorithmic challenge and how we solve it. Once we do that, then we can put that into use, because it's going to make our code a lot nicer, a lot more elegant than having to deal with it separately. So let us do that. Come back for the next video, which is also called x equals change x, and we will then continue on our way to look at algorithms to add items to trees and do the other kinds of traversals that we need to do. Again, very cool stuff. I hope you're excited about it. I'm excited to show it to you, and thanks for watching this video. Come back for the next, please.